Okay, good morning. We're going to finish chapter 12 today, and lab time is a worksheet on chapters 11 and 12. And then Wednesday, we will start up chapter 13, and then our last experiment is on Wednesday. Next week, we'll finish chapter 13. So on Wednesday, I'm not going to like speed through it or anything, but I definitely want to try and get through as much of chapter 13 as we can. Normally I, kind of try and cut the chapters in half pretty evenly and take some time. Wednesday though, I want to get through maybe more than what we would normally do, because the next Monday we'll finish chapter 13, and then that next Wednesday is the test. So I just want to make sure that you're not getting a whole bunch of new stuff and then getting tested on it the next class time. And then that following week, Monday is Memorial Day, so there's no school. And then Wednesday is the final. So we are, again, quickly coming to an end. I feel like it feels like we have a lot of stuff to do, but there's not a whole lot of time to do it. I'm sure you guys feel the same way with all your classes, but we're almost done. Okay. Questions at all on schedule kind of stuff before we start with lecture? Any general stuff? Get my little chat window up here. I did have a couple people email me about fall semester, so I'll just answer their questions for the class. People were asking about in-person versus online and what's going to happen. And the short answer is we really don't know. The long answer is that we are planning for our classes to be, we're planning for the chemistry classes to be in person, lecture and lab. And we are planning to be in person with full capacity, meaning whatever the capacity is for the class. So I think for us, it's 22. We're planning on having everybody in lecture and everybody in lab. Obviously, we don't know what's going to happen between now and then, if things hopefully are going to continue to get better. But if that's not the case and we have to go back to social distancing or increase social distancing or anything like that, then one option would be to have half capacity in the lab. So we would, since our class meets Monday and Wednesday, half the class would come to lab on Monday. The other half of the class would stay at home and do a worksheet. And then we'd flip the groups on Wednesday. It's one option. It's definitely not what we want to do, but it is an option. So yeah, short answer is we don't know. Long answer is we have all kinds of backup plans. So there you go. Not the best answer, but that's what we're working with. Okay. Where we're starting today is talking about protecting alcohol. So let me remind you what we just did last time. We talked about the Grignard reaction. And so in the Grignard reaction, we're starting with one of our carbonyls. We had a couple different options, and we're reacting it with a Grignard reagent. So it's a carbon group that has a magnesium atom, a magnesium metal atom, and either a chlorine or a bromine attached to it. And then that's going to do a nucleophilic attack on the carbonyl carbon. So we're creating a new carbon-carbon bond. One of the limitations of a Grignard reagent is that we can't have any acidic hydrogens. So we can't expose it to water, alcohols, carboxylic acids, pretty much any oxygen that has a hydrogen attached to it. So that is why water is added as a second step, not all at once. Okay, so there's your background, your reminders. So the example that's on this slide, it says, what if we want to do this? So here's our alkyl halide that we're starting with. And we're reacting it with magnesium to turn it into a Grignard reagent. Now notice that this says hypothetical Grignard reagent. This could not actually be formed because it has that alcohol group attached to it. So this is saying, what if we actually wanted to do this though, knowing that it's not possible? So then we react it with our ketone over here and we get our final product. Now, because we can't do this reaction, what this section is talking about is how to protect the alcohol. You can also think of it as like masking the alcohol or hiding the alcohol. So really we're doing a reaction so that the alcohol isn't an alcohol anymore. We finish what we want to do, and then we take the mask back off the alcohol. So let me show you what that means. Okay, here's the idea. This is obviously there's like a black box on here, but it's showing us kind of the general idea of what's happening. So with a protecting group will hide a functional group. So we're using it for alcohols here, but protecting groups get used often. And we'll talk about them a lot more next semester as well. So really what we're doing is we're taking that alcohol and we're turning it into something else. We're going to turn it into an ether actually. But so what this is showing is we're putting a mask over it. We're hiding it. We're protecting it. We do the reactions we want, and then we deprotect it, meaning we turn it back into that alcohol. So we have to protect and deprotect to start and end the reaction, and we do everything else we want in the middle. We do this for this reaction because of that acidic hydrogen. We do it in general because when we start to look at more reactions and we start to use bigger molecules, we have to think of the bigger picture. We can't just think, okay, this will react with this ketone, but what if there's also an aldehyde on that molecule? Will it also react with that aldehyde? We have to think of every functional group in that structure and which ones will react, which ones do we want to react? Can we hide one of them? So it's kind of a bigger picture, taking that next step idea. So here's what we're going to use for our protecting groups. So reaction number 6 is adding the protecting group, so PG, protecting group. What we use for a protecting group, we abbreviate it as TMS. TMS stands for trimethylsilyl. So it's a silicon atom with 3 methyl groups surrounding it. So the name makes sense. And so when we do the reaction, our oxygen, instead of bonding to that acidic hydrogen, it's now bonded to this TMS group. So that TMS group is now our protecting agent. So here's how the reaction looks. We have our alcohol down here, and I'm going to write it out a little more generic up here, but we have our alcohol. We're going to react it with, oh, I hit the pull button. Get out of here. Let's try this again. There we go. We're going to react it with TMS chloride. So really that just means it's bonded to a chlorine before it's bonded to the oxygen. And then our solvent is this. So a nitrogen. Oh, that did not look like an ethyl. Let's try that again. An ethyl, excuse me, a nitrogen with 3 ethyls on it. So triethylamine. I think we've used that abbreviation before. But there you go, in case we haven't. So triethylamine. And then we can write it as ROTMS. So that is our protected alcohol. Okay, so we know how to protect the alcohol. We now need to know how to remove that protecting group. So reaction number 7 is getting rid of the protecting group. So there's our protected alcohol. We're going to react it with acid and water, or, notice there's an or there, or a fluoride ion. The way that the fluoride ion is introduced in this reaction is with TBAF. So tetrabutyl ammonium fluoride. So tetrabutyl, because there's 4 butyl groups attached to that nitrogen. Ammonium, because when a nitrogen is positively charged, it's an ammonium group. and then fluoride because of the negative fluorine. So it might just be written as F- because that's really the part that we care about, or it might be written as TBAF because that's how we deliver it. That's the form that it comes in. So either one of those though, acid and water or TBAF, and then we get back our alcohol. Okay, so let's put all this together. So remember, we're going back to that original reaction that we saw where it said it was a hypothetical Grignard reagent. So we're starting with our alkyl halide alcohol. Now this is just one example of how to use this protecting group, deprotecting group. That wasn't the right way to say that. This protecting group reaction and then the deprotection reaction. And so again, we're using these because we can't create a Grignard reagent from a compound that has an alcohol group on it. So we start by protecting it. So this was reaction number 6. We're adding our TMS chloride, our triethylamine. And so now we have our protected alcohol. This reaction creates the Grignard reagent. So we would have BRMG, OTMS. And then these two are the Grignard reaction, which, let's see, that is reaction number 5 in our chapter. So after we do the Grignard reaction, notice that we still have that protecting group on our alcohol. And so then our last reaction here, we're going to deprotect. We're going to turn that alcohol back into an alcohol. So we're going to take off that TMS group. So this is reaction number 7, where we're using TBAF. And we get back to our alcohol. TBAF is definitely the more common one to use. We know that we've seen acid and water in a lot of reactions. So because of that, that means that a lot of things will react with acid and water, whereas TBAF is very specific. And so it's often more common to use something more specific so that it doesn't affect other parts of the molecule. Definitely depends on what's present in the molecule, but TBAF is going to be a pretty safe option for this. I know this is kind of a weird one, but any questions about this?
Are you going to do an example that's not generic?
I am. And I think, I do have a blank slide ready to go.
Okay, thank you.
Any other questions about that before we look at an example? Okay, let's do an example then. All right, this is the reaction we want to do. So this would be a multi-step reaction, multi-step synthesis reaction on the test, that style of problem, where we have to figure out all of the reagents we need to get there. When we look at what is changing, it's really right here. Our ketone is becoming an alcohol, and we've added on this ethyl group. So the ketone becomes an alcohol, and we add on an ethyl group. There's my little summary of my inventory. So when we see that a carbonyl group, a carbon-oxygen double bond, is becoming a single bond, we know a couple ways to do that now. That's what this part of this chapter has been focused on. But by adding on that carbon group, we know that it has to be a Grignard reagent. Remember, we only have 2 ways to add on carbon groups. We have our triple bond alkylation, and now we have a Grignard reaction. So when we see that new carbon group added on, it should definitely be the driving force for how you do the reaction, because we're so limited in how we can do that. Now we know it's going to be a Grignard reaction then. So this, essentially, this tells me that I need to do a Grignard reaction. But there's a big but here. The big but here is that there's a carboxylic acid group, and we can't do a Grignard reaction with that acidic hydrogen. So we have to protect that acidic hydrogen, do our Grignard reaction, and then deprotect it so that we get it back in the end. So here's how we're going to do that. I'm going to erase my underlines first of all. So I'm going to start by reacting this with TMS chloride in triethylamine. So there's my protecting group and my solvent. We're going to get OTMS. Oh, I got water on my screen. Sorry, gotta clean my screen here. I don't know what I got on it, but it's sticky. Okay, there we go. Okay, so we now have a protected carboxylic acid. So notice that we showed this with an alcohol on the last slide, or last few slides, but we're using it with a carboxylic acid. It still has that OH group, so it's still going to work. So this would work with carboxylic acids and alcohols because it still has that OH group. Now we can do our Grignard reaction. The other difference between the example we saw on the past slides and this one is our OH group was on the actual Grignard reagent itself, and this time our OH group is on the ketone molecule. So wherever that alcohol or that OH group is, it will need to be protected. So I'm going to react this with my Grignard reagent. I know I need to add on an ethyl group, so I'm going to use ethyl magnesium bromide. I could have also written this as ethyl magnesium bromide, both would be fine. And then in that second step, just water. My protected alcohol, still protected. Over here, we've added on our ethyl group and turned our ketone into a carboxylic acid. And then that last step is to deprotect, and we're going to use TBAF for that. So that's going to remove that TMS group and turn it back into an alcohol. So let me add a couple other little notes here. So this is adding the protecting group. This is removing the protecting group. And then this whole thing is our Grignard reaction. Questions about that? If we didn't use the protecting group, if we just tried to react this with our Grignard reagent, what would happen is that, remember, our ethyl is really just a carbanion. That carbanion would grab onto the hydrogen. So we would just end up with an ethyl, or excuse me, ethane. So CH3, CH3. And our, that's too high. I couldn't draw on the alcohol. I'm going to put it over here. Our carboxylic acid would just be missing its hydrogen. So if we don't protect that hydrogen or protect that alcohol group, then our Grignard alkyl, that anion, will just steal that hydrogen away. Yes, so in the chat, somebody asked if TEA is the same as ET3N. Yes, let me go back to where they're all written just so I can show you. right here. So TEA is this guy, which is triethylamine. So triethylamine, you could figure out what the actual chemical formula is for that. I don't know. The name, the abbreviation, the formula, either one would be okay. Any questions about this reaction? I know it's a little bit of a weird one. And it's definitely taking that next step, because we have to think about not just the reaction we want to do over here, but we have to think about how it affects the rest of the molecule over here. So it is kind of the next step up. So if it seems a little confusing or a little difficult, it makes sense why it would. It's not just as straightforward as some of the other ones. You don't need to know the mechanism for reaction 6 or 7, which was adding the protecting group and removing the protecting group, though. Okay, anything else? Okay, so we have a handful of slides for sections 9 and 10. And some of these are going to be review, some of them are going to be new, but all of them are substitution and elimination reactions. And if you remember back to last Wednesday, I said that in this chapter, they didn't number them like they normally do. So I numbered them myself, but it means that the way I numbered them in this chapter or in this section is maybe not the most effective, but it made sense to my brain at the time. So I'll show you what I mean by that as we look at the next couple slides. But reaction number 8 is SN1 reactions with alcohols. So this has to be a tertiary alcohol. So remember, that means that we're going to have our alpha carbon. So the carbon, this guy right here, that's my alpha carbon. The alpha carbon is going to be bonded to 3 other carbons. That's what a tertiary alcohol is. In order to do an SN1 reaction, we have to protonate the alcohol. So the example that's on here is with HBr. So here's our mechanism. We're going to use the hydrogen on that HBr to add a hydrogen to our alcohol group. So proton transfer, because then we create water. Water is a good leaving group. So water takes off, loss of a leaving group. So right here it says minus water. That's not something you would actually have to write on an arrow. Sometimes that's included and sometimes it's not. It's really just to say, this is what we've lost. We've lost water as a leaving group. And it's not used with all leaving groups. It's really used with water or bigger things. So I don't know. It's not a consistent way to display things, but it's definitely not needed. When that happens, though, we create a carbocation. So if you remember back when we learned about SN1 and SN2 the first time, SN1 always makes a carbocation, and it always happens in 2 steps. So we always have loss of a leaving group. We always have a nucleophilic attack. We might have proton transfers depending on what's happening. When we're using an alcohol, we will always start with that proton transfer to make it into a better leaving group. If our nucleophile is neutral, then we would also have a proton transfer at the end to remove its extra hydrogen. So we're doing a nucleophilic attack at the end here so that we can end up with our alkyl halide. So if we were to write this a little bit more generic, keep meaning to write an H. My brain is jumping ahead on me there. But that's all we would get. And so, and underneath this, we can just write it that it has to be tertiary for this reaction. Well, has to be tertiary for it to be an SN1. There we go. The one right underneath it is SN2. So reaction number 9, 9A. Notice we're going to have a lot of 9s here, but this is an SN2 reaction. So this is primary and secondary alcohols. And for this one, we're essentially doing the same steps. We're doing a proton transfer. We're doing a nucleophilic attack and loss of a leaving group. The difference, though, is that these 2 are going to happen at the same time. So the reaction, that generic reaction that I wrote up here, oops, is the same. It's just that when it's primary or secondary, it's SN2. When it's tertiary, it's SN1. So a lot of the same reasoning that we've seen in chapter 7, I believe it was. But yeah, so we just have to have that tertiary carbocation in order for it to form. Okay, so here's the next slide is going to show you where my numbering got a little weird in this section, but this was 9A. Notice the title, SN2 reactions. So we're still on reaction 9, but now we have 9B and C. All of reactions 9, because there's going to be a couple more, are all SN2 reactions. So that's why they're all grouped together. And there's really a lot of similarities here. They are just a little bit different variations. So in this one, we're reacting with HCl, and then we have zinc chloride as our as a catalyst in that reaction to help it go, because alcohols aren't the best leaving group. So by protonating it and having that catalyst in there, it's going to help the reaction. This only works, so this reaction is only going to work if we have 3 carbons or less. And then remember with our SN2 reaction, so this is SN2 in general, our stereochemistry is going to be inverted. So this won't affect primary alcohols, but it would affect secondary alcohols. It doesn't affect primary because there's 2 hydrogens, so there wouldn't be a stereocenter at that location. And then actually, since I said that, let me go back and add, remember with our SN1 reactions, the stereochemistry is approximately racemic. Okay. And then reaction 9C, so this is 9B, this is 9C. So we have our alcohol. We already know it's a bad leaving group. This is a reaction that we have already seen before. This is a reaction from chapter 7, but we're reacting it with tosyl chloride and pyridine. So down here is what pyridine is. So we abbreviate it with a PY. It's the solvent. It's a nitrogen-based solvent, though, which also means that it's basic. So when we specify a certain solvent, that usually means that it's helping to stabilize something or might be used to remove a proton, is in this case because it's basic. But the purpose of this reaction is to create a good leaving group. So it turns our OH into an OTS, or a good leaving group. And then, so it is showing it with a halogen here, but really this could be any nucleophile. So reactions 9A and 9B are to add on a halogen, replace the alcohol with a halogen. In reaction 9C, because we're turning that alcohol into a good leaving group, we could replace it with any nucleophile we want. And again, we've seen that one before. Okay, couple more. 9D and 9E. These are both very specific. They are still both SN2 reactions though, but we have SOCl2, which is thionyl chloride. And pyridine. And then we have PBr3, so just a phosphorus with 3 bromines attached to it. These are both going to do a substitution reaction, and the SOCl2 will replace the OH with a chlorine. The PBr3 will replace the OH with a bromine. So just very specific ways to add on that chlorine or that bromine, and our alcohol, because it's an SN2 reaction, does have to be primary or secondary. So we are going to look at the mechanism for both of these. For both or one? No, that is not true. Why do I have a spot for that? Oh, I took it out because I decided we didn't need to know it. I have it in my notes still, but I didn't fix my notes. Okay, you don't need to know the mechanism for this one. All right, so this did go up to 9E, and there's definitely repeats in terms of how to add the same thing. So adding a bromine or a chlorine, we have multiple ways to do that. And then there's also some repeats from past chapters. So these ones, because we aren't looking at the mechanisms and they're a little bit different reagents, these ones are definitely good flashcard topics because there's not a whole lot to understand about them. It's really just a memorizing the reagents kind of thing. All right, we've talked about substitution, SN1 and SN2. That means we have to go to the elimination side. So our first reaction in this section, actually it's our only one, I believe. I'm looking at my notes trying to figure it out. Reaction number 10, elimination. So we have E1 and we have E2 here. For E1, this will be tertiary alcohols. E2 can be any of them, meaning primary, secondary, or tertiary, depending on what the reagents are. So our E1, and this was on our last test, this is definitely a reaction from chapter 7, but concentrated acid with heat, heat helps us push it towards elimination, remember. We will get our alkene as our product. So we're starting with our alcohol. We're making an alkene. And our major product will be the Zaitsev, which remember just means that it's the more substituted alkene. With the reagents underneath, we're starting with our tosyl chloride. So this is going to make our alcohol into a good leaving group. And then we're reacting it with base. For our major product, if we use a small base, like OH, OET, our major product will be the Zaitsev. So the more substituted. And if we use a large base, like a tert-butyl group, then our major product will be the Hoffman, which is the less substituted. So that's, again, everything on this slide is a review from chapter 7, but because we are specifically talking about alcohols, we're including it in this chapter as well. So having that control over which side the alcohol goes to is really important for directing a reaction. So we'll do a couple practice ones, but I think I have, yeah, we have a couple more reactions to talk about, and then we'll do our practice ones. Before we move on though, questions about the elimination reactions at all? Oh, sorry, I'm dropping things here. Okay.
Question. So I know you mentioned the major would be the small, and it'd be Zaitsev. So looking at the reagent, would we just have to like kind of memorize that OH and OET would be on the more substituted side?
Yeah, so if your base has 3 carbons or more, we would consider it to be a small base. And so really that's the part you can memorize, is that if there's 3 carbons, I think I said that backwards, 3 carbons or less is a small base, and then more than 3 carbons is a large base.
Okay, thank you.
You're welcome. Any other questions on that? So small base is less than or equal to 3 carbons. Large base is greater than 3 carbons. The ones that I've listed on there are the ones that we see the most often. But of course, anything with a negatively charged oxygen and some carbons attached to it can be a base in this case. All right, we have just a couple reactions left. Oh, sorry, wrong way. There we go. Section number 10 is oxidation. So we did reduction reactions in the beginning. We turned ketones and aldehydes into alcohols. But now we're going to go the other way. We're going to turn our alcohols into ketones and aldehydes and carboxylic acids. So now we're looking at oxidation reactions, which means our carbon is gaining bonds to oxygen. So we're starting with a carbon-oxygen single bond, and we're creating a carbon-oxygen double bond. So that's why it's an oxidation reaction. We're gaining oxygen bonds. And we're going to look at this on different scales or different reaction levels. If we start with a primary alcohol and we oxidize it once, or with a less reactive reagent, we can make an aldehyde. If we oxidize that aldehyde, we can create a carboxylic acid. Or if we use a reactive reagent that can't stop at the halfway point, our primary alcohol will turn all the way into a carboxylic acid. So we're really not going to talk about how to oxidize the aldehyde into a carboxylic acid. So I'm going to erase that arrow. We'll talk about that when we hit our aldehyde chapter. If we start with a secondary alcohol and we oxidize it, we'll make a ketone. But notice there's a little red X. We can't go past that. We can't turn our ketone into a carboxylic acid. It doesn't work that way. And so notice what's highlighted in red. A primary alcohol has 2 hydrogens. And so in order to make it into an aldehyde, we have to lose one of those hydrogens. And then to make it into a carboxylic acid, we're losing the last hydrogen. So we're gaining oxygen bonds by losing hydrogen bonds. A secondary alcohol only has 1 hydrogen, and so it gives up that hydrogen to become a ketone. We don't have any tertiary alcohols on this list because there aren't any hydrogens, so it can't be oxidized. It is oxidized as much as it can be already. It has that single bond to the oxygen. And so we can't increase its oxidation level because there aren't any hydrogens to remove. All right, let's talk about how to actually do these oxidations though. So what we use to do the oxidations is chromic acid. So this is what chromic acid looks like. It is H2CrO4. A chromic acid is not very stable though. And so because of that, we have to make it in the reaction. And I bring this up and I'm showing you this slide because when we look at the next slide and we look at how these reactions happen, the way the reagents get written out is going to vary because of how the chromic acid gets made in the reaction. So one option on our arrows will be just to write chromic acid. And you could write the formula, you could write the name, either one would be okay. Another way to do it is to use chromium trioxide, so CrO3, with acid and water and acetone. Now, in the beaker, in your flask, it would turn into chromic acid, but we've just put all of those ingredients on the arrow, and then in the reaction, the chemistry happens. Or we can use sodium dichromate, which is this big monster, but it is Na2Cr2O7 with sulfuric acid and water. And again, in the reaction, those would all turn into chromic acid. All right, now let's look at the actual reactions. So this is reaction number 11. This is our oxidation of our alcohols. So notice how we're divided up here. Secondary alcohols, primary alcohols that are turning to carboxylic acid, and primary alcohols that are turning, turning into aldehydes. So these are written with chromic acid, or the first two anyways. So H2CrO4. These could also be written, I'm going to put our other options here, CrO3 with H3O plus and acetone, or Na2CR4, no, sorry, jumped ahead there. Na2CR2O7 H2SO4 and water. So writing this, or this all mean the same thing. They're all going to work for both of these reactions. They're all going to do an oxidation reaction. And they're all going to create chromic acid within the reaction. I know that sucks, that there's three things that all do the same thing and all mean the same thing, but that's just the way it is. All right, so what we get here is we're starting with our secondary alcohol, and we're oxidizing it into a ketone. Now, because we are using chromium, we're using a metal, we're not looking at the mechanism for this. It doesn't quite fit into the patterns of this chapter. It's more of an inorganic kind of thing. In the second one, we have a primary alcohol, and we're oxidizing it into a carboxylic acid. So notice that our primary went all the way to that carboxylic acid. It didn't stop at that halfway point. It didn't stop at the aldehyde. The one underneath it, though, we have a primary alcohol, and we're turning it into an aldehyde. So this one is getting a separate reagent. We're using a reagent that is less reactive. So because we want to stop it essentially at that halfway point of oxidation, we need to use something that's just less reactive. So we're using PCC. At the top here is what it is. So it's pyridinium chlorochromate. So we've seen pyridine in a couple reactions. The blue molecule over there, these are flipped in terms of structure and name, but the blue molecule is pyridine with a hydrogen added to it. So it's in its cation form, it's protonated form. So it now becomes pyridinium. And then chlorochromate, we have our chromium. So it's really a CrO3 with a chlorine attached to it. So it slows down the reaction. It makes it less reactive, which allows us to stop at the aldehyde, and it doesn't continue on to the carboxylic acid. Underneath the arrow, CH2Cl2, I'm sure we've probably seen that before, but let me just remind you in case it's been a while. This is methylene chloride. It is also called dichloromethane. So because it's called dichloromethane, it gets abbreviated as DCM. It's not an abbreviation I use because it's not one that I was taught, but I do see it every once in a while. It's a really common solvent, though. It's a solvent that we use just to clean glassware. Sometimes it's that common. If we used a secondary alcohol with the PCC, we would still get a ketone. Just a little side note, just in case that pops up on a worksheet, or you're wondering, since I think that one's easy letters to remember. Questions about any of these oxidation reactions? Okay, let's do a couple boxes here. There's definitely going to be more than one right answer for these. So we just talked about a handful of ways to do some of these. I have the annotation turned on though. If you would like to fill in a box with some reagents, I would greatly appreciate it. Anybody else want to be brave? Names are turned off. No one will even know it's you. All right, there's one more box. All right, let's talk about some boxes. Let's add some other options in, because remember, most of these have multiple ways to do them. So I'm going to start right to left, since that's how these are on here. So the first, let's see, let's use blue. So this is an elimination reaction. When we're forming an alkene, that's how we know it's an elimination reaction. So we have acid in there. Acid is definitely going to do the trick. We can add in some heat. Oh, that was not a pretty arrow, or not an arrow. That's a triangle, not an arrow. Oh, good. We got the last box filled in. Okay, so acid and heat will definitely do the job for us. And another option, an alternative to that, so I'm going to just put a big or right here. We could use tosyl chloride with pyridine to turn that alcohol into a good leaving group, and then just some base. So both of those will work. These were both reaction number 10. Okay, in the pink one in the middle, so we have two options. I'm going to cut this in half because these are two different reactions. We have hydrogen with palladium. I'm just going to look for my reaction numbers here. This was reaction number 2. And then we have lithium aluminum hydride with water, which was reaction number 4. And what these reagents are going to do is they're going to turn our ketone into our alcohol. So we need to have some reagents. We'll put another box over here that will turn our alcohol into a ketone. And so to turn our alcohol into a ketone, we're going to use one of our oxidizing agents that we just saw. So I am going to use CrO3 with acid and acetone. So any of our chromium-based ones would work here. So the sodium dichromate, chromic acid, PCC, any of reaction number of 11 would work here. Reaction 2 and 4 are great, but they're going to do the opposite. So this was a reduction, and this side is our oxidation. And then last reaction, we're turning our alcohol into a chloride. And so SOCl2, thionyl chloride with pyridine, definitely is going to work. I don't know what letter it is, but this is reaction number 9, one of our many number 9s. And then a big or here, because there are some other options. We could just use HCl, and the hydrogen protonates that alcohol, and then we do a substitution reaction with the chlorine. And then this is probably more steps than we need, but we could also do tosyl chloride with pyridine and the chloride, so like NaCl. Questions about any of those? Okay. We have, oh yeah, so I do have to clear out the annotation. Anyone want to stop me for a picture before I do that? Okay. We do have one reaction. Oh, I think we have 2 reactions left. Sorry. I think there's 12 in the chapter. How about we just say, here's our next reaction. So this is also an oxidation reaction. The ones we just looked at, reaction number 10, use chromium. Chromium is a heavy metal, which means that it can be poisonous, it's damaging to the environment, it's damaging to our health, it's damaging to wildlife if it's not disposed of correctly. And so because of that, any reaction that uses things that are difficult to deal with at the end, we try to come up with alternatives. And that field of chemistry is called green chemistry. So green meaning like environmentally friendly green. And so there's a whole field of reactions that are essentially alternatives to ones that have been used for a long time. And we know that thinking about things in an environmentally friendly way hasn't always been the way that we've approached things. I say we, but meaning, all the scientists that came before us. And so this is a way to do these oxidation reactions without using a heavy metal, without using chromium. So we have 2 on here. One of them is the Swern oxidation. So they get names because they're named after the people that figured them out. Actually, let me color code them. We'll do purple for the first one. So the Swern oxidation is this one. So notice that we're starting with a primary alcohol here. If we start with a secondary, which is definitely an option, we'll make a ketone. So we can start with either one. It just depends on whether we produce an aldehyde or a ketone. We're going to react it with DMSO and COCl2. So both of those are up here. DMSO is, there's a typo in that name. Just the E and the M got flipped there. But dimethyl sulfoxide. We've seen this before. It's popped up as a solvent. I think we talked about it in terms of a aprotic polar solvent option in our substitution chapter. And then COCl2 is oxyl chloride. And so we can see the formula for it up there as well. And then our second reagent there is the triethylamine. So that's the one that we can abbreviate as T. And so these are going to have an oxidizing effect, removing that hydrogen, turning that oxygen bond into a double bond without having any of those heavy metals that are present. Again, we're not looking at the mechanism for it though. And then the second one, let me get a different color here, is the Des-Martin pyridine oxidation. So again, we can start with a primary or a secondary alcohol, and we'll make either an aldehyde or a ketone. And we are using DMP and methylene chloride. So DMP is this business over here. So the name of the reagent is even named after the guy that figured this out. Or probably 2, there's 2 names there. But we have a benzene ring fused to another ring. We have this ester group on there. We have an iodine. The iodine is bonded to 3 oxygens, and then each of those oxygens is bonded to an acyl group. So we have an OAC. This part right here is the AC portion, the acetyl group. So it's a big bulky molecule, but it has those oxygens on there that can help with the oxidation process to turn our alcohols into carbonyls. And again, there's no heavy metals in this reaction. And so it's going to be a lot more environmentally friendly, and we won't have that nasty waste to deal with at the end of the reaction. Looking at my notes here to see if there's anything else, but I think I just have the reagents written down. Questions about either one of those reactions? Okay, so these do the same thing on paper that reaction number 10 does. They're all oxidizing reagents. It's just in real life, in a lab and not on paper. These ones are friendlier for the environment. That's the big bonus here. Okay, last reaction. I can say that with certainty this time. Reaction number 12 is the phenol oxidation. So remember, this is our phenol. It's a benzene ring with an OH group attached to it. We're going to use chromic acid. So notice it's written as this way, but we know that there's alternatives to that now. So we could write this as H2CR2. No, I'm sorry, H2CrO4. Or let's see, we have the sodium one, so we're missing CrO3. CrO3 with acetone and acid. So all three of those reagents are going to do the same thing because all three of them make chromic acid in solution. And what we get when we do this oxidation reaction is benzoquinone. So it's our 6-carbon ring with a carbonyl on opposite sides from each other. And so it gets a special name because it's a benzene ring with 2 carbonyls attached. If it goes through a reduction, we make hydroquinone. And so there's a little cycle here of reduction and oxidation. But really, the part that you need to know on this is that. You don't need to know this part over here. So it will turn into benzoquinone. So what's important to note about this is that the oxygens are opposite from each other. The word that we use to describe that is that we say that they are para. So you might have come across this with, especially as we do some IR discussions, this comes up sometimes. But when we look at a benzene ring, if we have groups that are right next to each other, this is ortho. And then if they are separated by 1 carbon, it's meta. And if they are directly across from each other, it's para. So it's a way to describe the regio locations of substituents. Those words can only be used if there's only 2 substituents on the ring though. So ortho, meta, and para. And I will remind you of those words again next semester because we will have some benzene chapters. Okay. This is what we know how to do. I like this map. It gets a little intimidating, but it's good. It's a good summary. There's stuff on here from a lot of different chapters as well. So for example, this one right here, that's our radical chapter. That's chapter 9. So chapter 10. Let's just go with radical chapter. I don't remember what number it is. We have some elimination stuff and some substitution reactions. So we have our chapter 7 represented in there. We know that our alkene reactions, I believe those were chapter 8. We have our alkyne reactions. Those I think were chapter 9. And then we have all of our new stuff. So turning ketones and aldehydes into alcohols, turning our alcohols back into ketones and aldehydes. And then some of that substitution and elimination stuff we also talked about in this chapter. We did learn how to make aldehydes and ketones before this chapter. when we started with an alkyne. Remember, we created an enol and then turned that into a ketone or an aldehyde. So this is a really big summary of a lot of chapters, probably like 5 chapters worth. And it definitely doesn't have everything on it, but it's a good representation of how to switch from one type of functional group to another. So what I mean by that is if you're presented with a multi-step problem and you're starting with an alkyne, but you want to make an alcohol, we might not have a direct way to get there. It might not be one step, but we know we could turn that alkyne into an alkene and then turn that alkene into an alcohol. Or we could turn that alkyne into a ketone and then turn that ketone into an alcohol. So this is essentially giving us a map of how to get from one thing to another. And we know, just like if you're driving or walking somewhere, there's always more than one way to go. Some might be a longer pathway, but you'll still get there. And then like for this one, for example, both of these pathways are 2 steps. So again, on paper, it wouldn't matter which one we take. All right, let me see how much time we have left. I do have a couple multi-step synthesis problems to practice. Do I have a couple blank slides? I just have one blank slide. We'll see how much space we need when we get done here. Okay, there's our reaction. So, you know, I like to start with a little inventory, counting some carbons. So we have 4 carbons. We have a carbon-carbon double bond. So just by looking at this, we know that we can react the alkene. We have a bunch of reactions to react the alkene with. We know we could also add a bromine on to carbon 1 or 4 because of one of our radical reactions. We could use NBS to do that, but that's about it for carbons 1 and 4. Carbons 2 and 3 are going to be where all the action takes place. Over here, 1, 2, 3, 4. We still have our 4-carbon chain. We've added on a new methyl group. So we've added on a methyl and we have an alcohol. So going through this reaction, we need to find a way to create an alcohol and add on a methyl group to our 4-carbon chain. Now we don't know a whole lot of ways to add on that methyl group. We know 2. And one of them isn't going to work. We know how to add on a methyl group if we have a terminal alkyne. We know that we could turn that double bond between carbons 2 and 3 into a triple bond, but it wouldn't be terminal. And even if it was terminal, the methyl is not added on to the terminal carbon. It's added onto the inside carbon. So that option's out. Let's get rid of him. The other way we know how to do that, though, is through a Grignard reaction. And so this is where I'm going to take a little bit of a retrosynthesis approach, because I know that if I can get a ketone at that spot, I can react this with a Grignard reagent and water in my final step. So having a ketone at carbon number 2, I can react it with a methyl Grignard reagent, and that would allow me to get that methyl group onto carbon number 2. So then we have to figure out, well, how do we get a ketone onto carbon number 2? Well, what we've learned in this chapter is we know how to turn an alcohol into a ketone. So again, there's a couple ways we could do this, but I think the fastest way, and definitely using new stuff, is to add an alcohol to carbon number 2 and then oxidize that to turn it into a ketone. So that's what I'm going to do here. So I'm just going to add acid and water. So that's a chapter 8 reaction. It's from the alkene chapter. I think that's chapter 8. And then a reaction from this chapter, we can turn that alcohol into a ketone. And again, we have a couple ways to do this, but I'm going to put chromic acid and water here. So any of our chromium-based ones or the new ones we learned, the SWERN and the DMP. So I think there's 1, 2, 3, 4, 5. I think there's probably like 6 different ways we could have done that last step, 6 different sets of reagents we could have used. Another way that this could have been done, let me grab a different color here. We could turn this into an alkyne. And then if we react that with acid and water, we get the enol, which turns into the ketone. So to turn that in, to go from an alkene to an alkyne, we could react it with Br2 and then excess NaNH2. And that would turn our alkene into an alkyne. So it's technically one more step because we have to make that dihalide and then create the alkyne, but it definitely works. It would do the same thing. For that last step, that's the only way that we know how to do that last step. So it's those first couple steps to get to that ketone that we have some options for. Any questions with that one? Okay, I'm gonna erase this and just use this slide again. So any questions before I do some erasing, or anyone want to tell me to slow it down so you can copy or take pictures? Okay, doing a bunch of erasing then. All right, so we're gonna look at one more. Starting with an aldehyde, we're gonna make a ketone. So we have a 4-carbon aldehyde. We have a 6-carbon ketone. So we're adding on an ethyl group essentially. Any thoughts on how we can turn our aldehyde into a ketone? So, oh, go ahead.
Chlorine.
I'm sorry, say it again.
Bromine or chlorine?
So bromine or chlorine, what do you mean?
Like by adding it?
Oh, and then doing like a substitution with it?
Yeah.
So we're kind of going to do that. We're going to, because we're creating a new carbon-carbon bond, so this bond right here is our new bond. And remember, those carbon-carbon bonds are the ones that we have very few ways to do. So we're going to have to do that with a Grignard reagent. And I have to have some type of carbonyl to do that. So that's what I'm going to start with. So we're going to use ethyl magnesium bromide. So by doing that, 1, 2, 3, 4, there's my new ethyl group that I just added on, carbons 5 and 6. I have the right number of carbons. And then we're going to do one of our oxidation reactions. So again, I think we have 6 sets of reagents to write this out. We will do CrO3 and acid with water and acetone. And it will oxidize that alcohol into a carbonyl. So essentially we did two things. We added on our carbon group and then we reoxidized our oxygen into that carbonyl, into a ketone this time. I was trying to think if there's a different way to do this. I don't think we know any other ways to do this. I'm sure there's another way. Because I was thinking if we reduced this, if we reduced the aldehyde to an alcohol and got it into an alkyne, then we could add on those carbon groups and then react it with some acid and water to get the ketone. Wouldn't be the best way, but it could happen that way as well. Any other questions about this one? Okay, that is it. That is the end of chapter 12. So I think we're done a little early here. I'll hang around and answer any questions you might have. But lab today is a couple worksheets, so chapter 11 and 12 worksheets. So I will see you in lab, but feel free to hang out and ask any questions you might have.